to show you how to graph a quadratic without a table of values. What you're looking at here is y equals some number times x minus some other number squared plus yet another number. So these three numbers here, which I have labeled as letters, a, h, and k, a indicates a vertical stretch. So if you have, for example, a 2, then things are stretched vertically by a factor of 2, which would make your quadratic twice as tall. The h represents a horizontal shift. So notice that you have a negative here. If you have a negative 2, that will shift it horizontally by 2 units in the positive direction. That would be to the right. And that k is a vertical shift. So any quadratic is going to resemble y equals x squared, that basic quadratic that you know very well. And then if you apply these three transformations to it, you can determine what the one you are graphing looks like. So let me show you a few examples here. So consider this one. Let's say we've got y equals 3x squared minus 2. And I want to draw the graph of this without doing a table of values. You know very well what y equals x squared looks like. Y equals x squared goes from the origin and goes through the points 1, 1, 2, 4, 3, 6, and it looks like that. The 3 that you see here is a vertical stretch. That means that each point is stretched vertically by a factor of 3. So if I was to, and in blue, I'm going to pretend that there's no minus 2 there. So in blue, I'm just going to look at y equals 3x squared. It's going to look just like y equals x squared, except it's going to be 3 times as high at any point. Notice they have the same origin because if you multiply 0 by 3, you just get 0. But instead of going up 1, it goes up 3. Instead of going up 9, it would go by up 27. It's 3 times as high. However, that minus 2, if I want to incorporate that minus 2, it is a vertical shift. And what that means is the entire thing is shifted down. So to graph y equals 3x squared minus 2 without a table of values, I'm going to take the origin and I'm going to shift it down 2 units, which is going to put me here. And then as I make my way up, I'm going to be 3 times as steep because we have a vertical stretch by a factor of 3. So this thing is going to look like this. So rather quickly, I can get this sketch without needing a table of values. So let me do a couple more examples. So let's say we have y equals negative 2x minus 3 squared plus 1. Okay. So now I have a vertical stretch by a factor of negative 2. A horizontal shift, so let me just remind you here, with y equals ax minus h squared plus k. A is the vertical stretch, h is the horizontal shift, and k is the vertical shift. So I've got a vertical stretch of negative 2, a horizontal shift of negative 3, and a vertical shift of plus 1. So this will look just like y equals x squared. So this one here is y equals x squared. But I need to give it a vertical stretch of negative 2. Now the negative makes it upside down, and the 2 makes it twice as tall. So this one here, that's stretched out doubly and is upside down, that is my negative 2x squared. So if I was to just apply the -2 to y equals x squared, it would give me that. We have a -3, which means we have to shift this 3 units to the right, and a +1, which means we have to shift this 1 unit up. So our final result, it is going to be shifted 3 units to the right, 1, 2, 3, 1 unit up, and it's going to be a quadratic that is upside down, and it is twice as tall as y equals x squared. So it's going to look like this. So I can erase that intermediary one. And I've now sketched this quickly without a table of values. So let me recap. Any quadratic will resemble in shape y equals x squared. These numbers here correspond with transformations to y equals x squared. This first number, the -2, means that the negative flips it upside down and the 2 stretches it vertically by a factor of 2. The -3 shifts this 3 units to the right, and the +1 shifts this 1 unit up. That gives me the image of the graph without having to resort to a table of values.